Rocky outcrops in quarries give geoscientists a location to glimpse the framework of our Earth. Like the tip of an iceberg above the water, hinting at what lies below, these exposed rocks offer a fraction of what is hidden underground. In Earth's unseen underground world, certain rocks are more than just stones, they're vaults of potential. Among them is this highly porous limestone, keeper of billions of dollars in resources, and with the potential to redefine our energy future. But how do we find this treasure, and why is it so crucial? In the expansive archives of the Oil, Gas, and Salt Resources Library, explorers can delve into thousands of rock samples. Rock cores like these are collected from underground by specialized drilling. They offer a high-resolution glimpse into the subsurface, akin to standing at a narrow rock face. When cores are not collected from drilling, explorers can collect cuttings. These are small samples of smashed-up rock that help fill in the gap between cores. You and other explorers can analyze rock cores to find hidden resources. These are sedimentary rocks, deposits of materials brought about by natural forces of the ancient environment. This could be the bottom of a sea, lake, or river, a windswept desert, a glacier, or a lagoon, which sets the story of how these rocks will transmit fluids. Decoding the ancient past, as it was set in stone, informs us of the resource potential today. Sedimentary rocks can be organized into three broad categories based on their origins: clastic, chemical, and organic. Shale is an organic type of rock. In the hands of an explorer, shale tells of deep marine environments where fine-grained sediments accumulated over time. This environment has created a rock that is usually acting as a geological seal to fluid movement due to its fine and tightly compacted matrix. It can also be rich in dark organic material from its marine origins and act as a source rock for oil and natural gas. Microscopically, this dark organic rich shale has compact layers hinting at a steadfast resistance to fluid flow, revealing a nature that is both dense and impenetrable. Limestone and dolostone are chemical rock types predominantly formed in a shallow marine environment from the accumulation of carbon-rich materials, like the shells of marine organisms. Being born of compacted marine remnants endows these rocks with pockets to trap fluids, a natural porosity. Under the right conditions, dissolution of its soluble components can create a good reservoir. Paradoxically, alterations and minerals precipitating into its pore space may transform the rock into something less permeable. Use a microscope to be sure. This is a porous limestone. Embedded within its matrix, an intricate fossil has many chambers, illustrating the rock's ability to house fluids. Sandstone is a clastic rock birthed from sand-grain-sized materials. Its structure may have a well-integrated network of pores and fractures, if they aren't cemented shut. The structural features are the result of ancient energetic landscapes, like wind-swept deserts, meandering rivers, or coastal regions shaped by persistent currents. Explorers will need to examine the space between grains to read how fluids will move through these layers. See the individual grains of sand under the microscope? Its interwoven grains and open channels signal a readiness to usher fluids through its structure, acting as a conduit in the subsurface world. Salt is a type of chemical rock formed by the complete evaporation of a sea. Its presence sends a special signal. Fluids have not moved through this zone to rinse the salt away. Crystals of salt look very similar to your table salt, which may have come from this very rock unit in Ontario. Each type of rock has frozen in time, the nature of the environment that it was formed in. The environment sets the stage for how much fluid a rock is likely to hold, the porosity, and how easily fluid can move through those rocks, the permeability. Rock type alone did not reveal to us explorers the whole story of how fluids move through these rocks. Close examination and testing of cores informs us on fluid movement at one well, allowing extrapolations to other wells, like those with cuttings. Let's return to the original core and examine this piece in detail using our knowledge of rock types, porosity, and permeability to determine why it is so valuable. The limestone specimen boasts a significant network of large pores that we know are connected from examination and testing. This is an excellent rock for both storing and transmitting fluids. This core hails from an underground rock formation near Sarnia. Rich in natural gas and oil, the deposits within this rock were readily extractable, owing to the fluid's ease of movement. However, this merely scratches the surface of the rock's energy potential. After the reservoir was depleted, the rock's void space emerged as an invaluable asset, serving as a secure storage for vast quantities of natural gas for use at moment's notice, with potential stretching to new horizons. Envisioned as a colossal battery deep in the subsurface, it could accommodate innovations like compressed air energy storage, bolstering clean power generation, or house hydrogen for transport solutions. Moreover, by understanding pore space, we can harness it for carbon dioxide sequestration in some rocks, or other storage concepts yet to be conceived. Deciphering the tales of ancient environments from rock samples and disseminating this knowledge through repositories such as this has enabled the mapping of these concealed formations. While the journey began with oil and natural gas, its horizon now encompasses diverse applications with enduring potential.